today's presentation. My name is Shangyang Li, and this is the OTFS SIG online seminar series. And today we are very happy to have Professor Lei Liu from Zhejiang University to be here to talk about the new advancements in IFDM. And this online seminar today is organized by me, Weijie, Zhiqiang, and Professor Tang and Professor Gong. And both of them are from Beijing. And thank you for your support. So if you are interested in this mailing list, you can join us from these web pages, and these are some links that you may find useful. Okay, so without further ado, I'm going to introduce the main topic of today's talk. There will be interleave frequency division multiplexing presented by Professor Lei Liu. I'm going to give a quick introduction of Professor Liu, sorry. Professor Lei Liu received a PhD degree from Zhejiang University in 2017. From 2014 to 2016, he was an exchange PhD student with Nanyang Technology University, Singapore. From 2016 to 2017, he was a postdoctoral research fellow with the Singapore University of Technology and Design. From 2017 to 2019, he was a research fellow with the City University of Hong Kong. From 2019 to 2023, he was an associate professor with the Japan Advanced Institute of Science and Technology. He is currently a Zhejiang University young professor. I think this is a very prestigious title from the Zhejiang University, and his current research interests include wireless communications, message passing, statistical signal processing, modern channel coding, and information theory. Okay, please join me to welcome Professor Liu for today's speech. Thank you.
Hi, can you hear me?
Yes, very good.
Okay, thank you. So thank you, Shuang for your nice introduction, and hello, everyone. First, I would like to thank Dr. Shuang Li and Professor Pan Tang for kind invitation. And I'm Lei Liu from Zhejiang University, and it's a pleasure to share our work on interleave frequency division multiplexing with you. So let me share my slides. Okay. Can you see my slides? Can you see my slides? Shuang?
Yes, very clear.
Okay.
Thank you.
Okay. Thank you. So this is a joint work with Dr. Yu Haozi and Professor Yin Li from Zhejiang University and Dr. Ge Yao from Nanyang Technological University and Professor Zhaoyang Zhang from Zhejiang University. And there are two references for this talk. The first is IFDM published in IEEE Various Communication Letters. And the second is a memory MP published on the IE transaction on information theory. This is the outline of my talk, and this figure outlines the main structures of this talk, and it is linear. We focus on linear systems. There is a linear multiple input and multiple output here. So this system model, there include many applications for example, the static or time variant multiple path channel, and MIMO multi-user or multiple access channel, and source random access, and so on. So we will focus on the four parts of this linear communication systems. The first is the modulation. We will propose interleave frequency division multiplexing. And after that, I will introduce the memory approximate message passing detection for the IFDM systems. And as you know, the current encoding and decoding are mainly focused on the single input and single output channels, and we already approaching or achieving the CISO AWGN channel capacity. However, for the linear systems, the CISO coding schemes is suboptimal. So therefore, how to design a code or how to design the code encoding and decoding to approaching the capacity of a linear systems is still unclear. So in the last part, I will introduce the capacity optimal coding principle for the linear systems. So first is the modulation IFDM. So let's start with the multipath channel. So multipath channel is given by this figure. There are director paths and some delay paths, and this can be described by this formula. And then we insert some cyclical prefix, and then we remove the CP. Then we can get a equivalent system like this. And here the equivalent channel matrix of the multipath channel it has a spatial structure that is the named top this structure, and it has a structure like a cyclic shift. And for this spatial structure, there is a spatial decomposition given by this, similar like the SVD decomposition. And we can see like that the left matrix is IDFT and the right matrix is DFT. But in the center, there is a diagonal matrix. And this is the OFDM. Then is OFDM. OFDM is used to deal with the multipath channel, and it can be described by this diagram. And the principle of OFDM is that we insert a modulation here, use a IFDM matrix, and then we input a channel H, and at the receiver side, we use a FFT as the demodulation. Why we do this? So things as I mentioned, the multipath channel, after we include the CP and the CP as the equivalent system, then the equivalent channel matrix can be decomposed as this. So we can subject this to this system model, and we can see like the FFT matrix can be eliminated and the receiver side and the transmitter side. Therefore, we get an orthogonalized equivalent system. So this is an orthogonalized equivalent system. This principle is similar like we make we have a convolution in the time domain, and we get a product in the frequency domain, and there is no interference in the symbol interference in the frequency domain. So we can get a symbol by symbol minimum mean square error detection. So as you can see, S1, S2, Sn, there is no interference between these symbols. So then the question, so why we need OFDM? So the answer is quite clear. There is no interference, and the receiver is quite simple. But the question is, how about the performance? Unfortunately, the performance is not good. Let me show you an example. We just consider a very simple two-dimension orthogonal systems, and this is the orthogonalized diagonal matrix, is the channel matrix, and this is the singular vector, and we just focus on QPSK singular vector, and then we can move the equivalent channel to the noise, and then we get a smaller noise with a scaling factor 2/3. And we also get a larger noise for S2. Let me show you a figure. So this figure, this red point is the constellation point, is denotes the symbol vector, and the blue lines denotes the noise pattern. As you can see here, the noise of S1 and S2 is asymmetric. So as you can see, the noise in the S1 dimension is small, and it's very hard to have occurs error from this point to this point. But in the S2 dimension, the noise is larger. Then there is a high probability to have a error from this point to this point. So there's a overlap between between this area and then high error probability. So can we do better? The answer is we can do a modulation to solve this problem. So the modulation can be described by this formula. That is, we introduce a unitary or rotation transform matrix cosine, and so before we transmit the matrix symbol S, then we do a transform uniform transform, then we input to the channel. So if we choose different unitary matrix or new unitary transform, then we get different modulation. For example, if this is the identical matrix, then we obtain the OFDM modulation. And similarly, we can move the channel and the transform to the noise, and we can see like we get a equivalent system. Equivalent system is something like we make a transform to the asymmetric noise vector. And since this is a unitary transform, so the amplitude of the noise vector will not change, but it only changes the phase. So we can take an example of the 45-degree rotation matrix as an example. And after we use this rotation matrix, we get a new results. That is the error pattern. The noise pattern is look like this. There is rotated with 45 degree. So if there is no unitary transform, then we get this asymmetric noise pattern. But after we do a 45-degree rotation, then we get this figure. As you can see in this figure, this point is very hard to have an error to go to this point, right? And they are from this point to this point, this point to this point, they are symmetric. The noise pattern is symmetric, so both of they are safe. Then we can get a better performance since we get a symmetrical noise. This is the BR performance of these two different schemes. So this is the SNR, and this is BR performance, BR, and this is the BR performance use Mercury likelihood detection, and the performance look like this. It's also OFDM system. And this is the performance of the system with 45-degree rotation. And we can see that this scheme has 3 dB gains named OFDM. So it means like the OFDM is not good in performance. So then there's another question. So in the 2-dimensional case, we can always find a good rotation matrix by exhaust searching, right? But how about in the high-dimension systems? So it's very hard to choose a good rotation or unitary matrix. So if you do the exhaust searching, the complexity is too high. So our answer is like a random unitary matrix or rotation matrix is good in high probability for high dimension signalings. So let me show you an example. So we do some tests, we do some experiments. So we randomly generate 100,000 unitary matrix cosine, and and the diagonal matrix lambda, and given the distribution of the lambda. Okay, then we see the simulation results for the different unitary transform matrix, and here this line, this is the black line is the performance of the OFDM systems. The performance is poor, and there is this is a replica limit, is a system limit of PR performance limit given by this, and the red line is the performance of the different unitary transform matrix with AMP detection. So if we find a good unitary transform matrix, then we get a good PR performance. But if we find a bad unitary matrix, then the performance is poor. And this is the likelihood detection performance for different unitary transform functions, transform matrix. And we can see that ML always performs better than the AMP detection. And this simulation is done on the singular dimension equals to 8. So then we increase the dimension. We let the singular the dimension of the singular vector goes to 16, and then we can see some interesting. We can see like both the performance of AMP and the likelihood detection move to the left, closer to the replica limit. Then we let the system go to 40, 32, and 100. Since this is very large, the system is large, and the likelihood detection has a high complexity, and it is unavailable for the length equals to 32. This is a 128. Then this is 500. In 500, we can see like the performance of AMP detection with the unitary transfer functions approaches the replica limit, and all the different almost all the unitary the performance of the unitary matrix are close to the replica limit, but the OFDM still has a poor performance. So this is a conclusion. So as the dimension increase, we found like the BR distribution of the AMP detection is concentrated. Okay, and the performance of AMP detection approach to the replica limit, and the OFDM always has a poor performance. So that is the conclusion. So it means like a random unitary matrix is good since it's approaching the replica limit in high probability. Since when the dimension is very high, all the unitary matrix are located close to the replica limit. So for the high dimension singularities. So this solves the problem. How to choose a unitary matrix? It means that it just randomly generate a unitary matrix. Then it is good in high probability. But for the practical implementation, how to choose a specific unitary matrix? So our answer is IFDM. IFDM is given by this. We designed the unitary matrix by permutation of FFT matrix. So why we choose this? It is very simple. It's just OFDM plus Interleave. And the Interleave ensures the randomness of this matrix, and it's very easy to realize. Why we choose FFT? First is similar to the OFDM systems. The second is that there is a fast Fourier transform algorithms to realize this transform. So then we go to the 10 variant multipath channel. In the 10-variant multipath channel, we can imagine that imagine this case. So the transmit is moved with a space with a speed v, and this is a director path, and then this is some delay passes. And the problem is like in the 10-variant multipath channel, the element in the channel matrix is changes with 10, as you can see here. So this the equivalent channel is not cyclical shift anymore. So we cannot diagonalize this channel matrix use OFDM. So the OFDM is inefficient. So as you can see here, so if we use OFDM for 10 for the 10 variant multipath channel, then you can see the equivalent channel in frequency domain is not orthogonal anymore. Now to solve this problem, the OTFS and the AFDM are proposed. And I don't go to the details of the OTFS and the AFDM. So I just show some key properties of the OTFS and the AFDM. So OTFS is just do some unitary transform by this modulation matrix, and then in the receiver side we also do a demodulation with this matrix. Then we can get an equivalent sparse channel matrix in the delay-Doppler domain, as you can see here. And for the AFDM is similar, but the AFDM use a different modulation matrix here. This is different from the OTFS, and also they involves a different a demodulation matrix and the receiver side. And after that, we can also get a near sparse equivalent channel matrix, as you can see here in the affine frequency domain. The problem of OTFS and AFDM is that there is no efficient non-orthogonal detectors, and I will show you some simulation results in the next. So IFDM is different from the OFDM, OTFS, and AFDM. As you can see, this is the block diagram of IFDM systems. We introduce a random notation matrix here, and as you can see, we first do a IFFT, and then we do a permutation or interleave here. So and as the result side, there is a FFT and de-interleaver here. So if we remove the interleave and the interleaver, this system go back to the reduced to the OFDM convolutional OFDM systems. But here we introduce a interleave here to ensure the randomness of the this modulation matrix. And so why we do this? As you can see, we can get an equivalent random matrix in this domain. Is the IF domain, is the interleaved frequency domain, and it looks like this is a random and dense. It's not sparse anymore, but random and dense. So based on this, so each symbol element can undergo all the channel elements, so we can ensure the diversity of the system. So as a result, we can get a statistical stable performance of the IFDM. So this design principle is much different from the OFDM, OTFS, and IFDM. So here is some closely related works. The first is the to be frank, IFDM is not a first or original discovery. So there have been similar and even identical works before. So we were unaware of these earlier contributions when we proposed the IFDM. So it is only after completing our work that we become aware of these earlier works. So therefore, we are happy to credit these earlier works with original introduction of the concept of IFDM. So the first work is proposed by Professor Liu. They introduce energy separating transfer function at the transmitting site. You can see here, this is the energy separating transfer function. And this transfer function look like this. There are some interleavers P, and also there are some unitary matrix U here. And the second is given by this work by some Chinese researchers, Li Dong, Wu Yanbo, Tao Jun, and Zhu Ming. They propose a transmitting structure like this. So here is a Hartmann transform. Then here is an interleave, and here is IFFT. IFFT is the same as OFDM systems. In this work, they focus on the 10 invariant multipath channel. So why you consider this channel? Since they want, since in the 10 invariant multipath channel, they can use IFFT and FFT to diagonalize this channel matrix. Okay, then he can get a low complexity VAMP detection here. The most similar or identical case is proposed by Yuan Xiaojun, Ma Junjie, and Li Ping. As you can see, actually, I was a postdoctor of Professor Li Ping. And you can see in his system, the transmit is exactly IFDM, is a FFT followed by interleave. It's very similar, but we use IFDM here. But this is similar. So it uses a large IFDM for multipath channels. There are multiple channels. There are multiple channels. So one sequence goes to multiple channels here. And at the receiver side, they use a high complexity MMSE. It involves matrix involves here. So this work focus on the MIMO channel, not the 10 variant multipath channel. So this work are very close to IFDM. Actually, this is the same as IFDM. So next is the memory approximate multipath detection. So the challenge is like now in IFDM, the equivalent matrix is dense and random. So dense means that there is high interference in IFDM, right? Then how to do the signal detection is challenging. So therefore, we propose the low complexity and the base optimal memory MP to do the signal detection for IFDM. So IFDM memory MP works on a very simple linear system model. This is y equals to hx plus noise, and this is the channel matrix, and this is the signal vector. And here, this is the signal vector follows a distribution. For example, discrete signal distribution such as Quan and QPSK. For general H and non-Gaussian X, so this problem is generally empty hard. So next we introduce some assumption. So if we consider a very large system, large scale system, such as the system size goes to infinity, and we assume that this channel matrix is right unitary event. This means like, what is that unitary event? It means that the H can be decomposed by these two matrices, and this is the given matrix. And here V is a par-distributed random matrix, and the V and this H is independent. So the target is to, given these conditions, Y and these constraints and these constraints, and the channel matrix, we want to recover find the MMSE estimation of X. And there are many applications of this system model, including compressed sensing, MIMO multi-user systems, modulation, and channel estimation, and size, even FEC coding. So AMP algorithm is the state-of-art method to solve this problem. The first is the AMP algorithm. I will don't go to the details of this algorithm. The first, I just briefly show the key point of this method. So the first is the AMP. It's very simple. It's just given by two formulas. And as you can see, it only involves matrix vector multiplication. And this is also often to solve the correlation problems between the iteration during the iteration between these two local processors. And it can be proved that the AMP is Bayes optimal. It can converge to the global optimal performance under the condition that the state solution has a unique fixed point. However, AMP is limited to IID Gaussian matrix. For some correlate or ear condition channel matrix, AMP has a poor performance. So to solve the problem of the matrix limitation of AMP, and Professor Yiping, Ma Junjie, and Langdon proposed the OMP and VMP to solve the IID limitation of the AMP. It is given by these two formulas. It's a little bit complicated than AMP. But the problem is that it involves a large scale matrix involves and has a high complexity. So, but it works for general unitary invariant matrix, and it can also ensure the replica-based optimal performance. It can converge to the global optimal performance under the certain conditions. But the limitation is that it requires high complexity MMMC. And here is a simulation result for ear condition channel matrix. And this is the AMP, has a poor performance. And this is OMP, has a very good performance and converges to the base optimal performance. And to solve the limitation of AMP and OMP and VMP, Keigo Takeuchi from Japan, he proposed the convolutional AMP to solve this. As you can see, this structure is very similar to AMP, but it uses a new orthogonal. It's something like a convolutional structure of the memories to solve the correlation problem in the AMP for the general unitary invariant matrix. So there are many good properties of the AMP. First is it is also Bayes optimal, converges to the global optimal performance if it converges. And it works for general unitary invariant matrix and has a very low complexity since it also only involves matrix vector multiplexing multiplication. But the problem is that it has a convergence problem. That is, this optimality is based on the assumption that the algorithm is convergent. But as you can see here, if we let the condition number of the matrix goes to increase larger than 15, then the performance of CAMP diverges. So as you can see, AMP limited to IID matrix, OMP and VMP has a high complexity, need a high complexity matrix involves, and CAMP fails to converge. So our question is, can we design an algorithm for all? It means that we want a Bayes optimal performance and work for general unitary invariant matrix and has a low complexity and ensure that it is convergent. Therefore, we propose the memory AMP. So I will also don't go to the details of memory AMP. I will just show you the key properties or the key structures of the memory AMP. So first is the memory AMP framework. Different from the non-memory OMP and VMP, we consider memory AMP structure. That is, this is the linear constant, and this is the nonlinear constant, is the distribution of X. Then we use a linear estimate for the linear constraint, and we use a demodulator, a nonlinear estimate for the distribution of X. And then we do the iteration. The key point of the memory MP is that it's not only use the current estimation in the iteration, for example, XT, but it use all the memories. For example, XY is the estimation in the first iteration, and the X2 in the second iteration, and the XT in the current estimation. And we use all the estimations to do the estimators vectors to do the linear estimation here. And also we use all the estimators of the linear estimate to do the nonlinear estimation. So this means that we use all the memories in the iteration to do the local processors. And here F is the error matrix of this estimation, and G is the error matrix of this estimation. And to avoid the correlation problem in the memory AMP framework, we introduce a stricter matrix orthogonality. That is, we require that the errors, these errors should be orthogonal to the true signal, and we need the error matrix output error matrix should orthogonal to the input error matrix. So it's given by this. So actually, this structure or this memory structure unifies the OMP and VMP, AMP, and CMP. Since all these structures can be unified by this memory AMP structure. And but the challenge is that memory make the correlation problems more complicated. So therefore, we use a for orthogonalization. For orthogonalization, that means we need the error matrix of each input and output error matrix of each local processors should be orthogonal, not just the step-by-step orthogonalization. So based on this framework, we propose a specific-based optimal memory AMP algorithm. This is given by these formulas, and I don't go to the details. So I will just show you some intuitions of this algorithm. First is that since the constraint, the nonlinear constraint here is simple symbol by symbol, so we still use the symbol by symbol non-memory orthogonal demodulation, and the same as the OMP and the VMP, so it has a very low complexity. But we use a memory match filter. Now we don't use a high complexity MMSE, as you can see here. We use a memory match filter. Memory match filter means that we use all the memories to do the estimation here, and you can see here it only involves matrix vector multiplication. So the complexity is almost similar to the AMP. Okay. And here the memory match filter here is actually a parallel expansion of the linear MMSE. So we can approach the global base optimal performance use a low complexity memory match filter. And here are some parameters, epsilon and p. These are some ensured orthogonalization in the memory MP framework. And also we use a damping, analytical optimal damping here to ensure the convergence of the memory MP algorithm. So here is the complexity comparison between the memory MP and the AMP and OMP and VMP. So OMP and VMP has a very high complexity. It needs MMSE. But AMP, CMP, and VMP has a very low complexity. So MN is the system size of the channel matrix, and the T is the number of iteration. And this is the space complexity is almost the same as the channel matrix H. So this is the main theory of the memory MP. And so assume that we consider a very large system and the matrix is relatively invariant, then we can prove that memory MP converges to the replica map optimal is the maximal posterior BR performance and the assumption that the state evolution has a unique fixed point. So the intuition is that we use the orthogonality to ensure the correct state evolution. And we use stamping to ensure the convergence of the algorithm. And we use a low complexity metric filter, memory metric filter to approach or achieving the local linear MMSE. And finally, we prove that the state evolution fixed point of memory MP is the same as OMP and VMP. Since OMP and VMP has been proved that it is replica map optimal, therefore MP is also replica map BR performance optimal. So next, let me show you our journey to IFDM. As you can see, memory MP want to solve this problem, but for journal metrics and journal signaling, this is MP hard. So VMP, OMP, and the memory MP are state-of-art algorithms to solve this problem, and it has a low memory MP has a low complexity, and it's based optimal, and it requires for large-scale systems, and can work for non-Gaussian signaling. They are very good performance, right? Has a good performance and has good properties, but it requires that right unitary invariant channel matrix. That unitary invariant channel matrix, it requires a decomposition like this. We need a random matrix V that is independent of the decomposed matrix H here. But in practical channel H, this is actually not right unitary invariant matrix. Therefore, we have if we directly use the memory MP or OMP, VMP for this system, there is performance loss. Let me show you an example. So here we consider a MIMO multipath channel, and we consider QPSK signaling, and this number of subcarriers is 1,000. And first we consider that there is no modulation. We just use no modulation. Since this is multipath, so we still have a symbol interference, and also like MIMO interference. And we use OAMP to do the detection of the multipath MIMO channel. Then we get the BR performance or MSE performance by this curve. But if we do the state evolution analysis, we can find that the state evolution of the AMP algorithm for this system is given by this point. So, but there is a huge gap between the theoretical results and the simulation results. The key point is that the channel is not right unitary invariant matrix, so the state evolution is not correct for the non-right unitary invariant matrix. Therefore, it has a huge performance loss. So how can we do? So we propose IFDM. So before we transmit the symbols to the channel, we do a IF transform. IF transform means that we use interleaved IFFT transform for the signal symbols vector S, and then we can get an equivalent match system model given by this, and so this is IFDM. So we can get an equivalent channel matrix by this, right? This is real channel matrix, and this is the modulation matrix. We combine these two as the equivalent channel matrix. Then this effective channel matrix is approximate right unitary invariant. Then we just do this, do the signal detection based on this system model, based on this system. Then we can see like we use a IFDM and use a low complexity memory MP. Then we get a simulation result performance by this red curve, and it is perfectly matched with the theoretical state evolution. So this is our journey to IFDM, and next is the closed domain memory MP for IFDM. So the cross-domain memory MP is motivated by Dr. Shuangyang Li's work, cross-domain iterative detection for OTFS modulation. It is given by this block diagram. So here there are two transforms deal with the interleave frequency transform here. And here we do a symbol by symbol demodulation for S, since S follows or Quan or QPSK. So since this is symbol by symbol, the complexity of this part is quite low. Is almost the same as as the names as the almost the same as the names of the signal vector and the point iteration. And since here we have a faster transform algorithms, the complexity of FFT and IFDM is n log n, so it is still also quite low. But in the 10 domain, the multipath channel or the 10-variant multipath channel, is very sparse. It's a very sparse channel matrix, and each node of the channel matrix has p non-zero entries. And here we consider a memory match filter. Memory match filter means that we only involve matrix vector multiplication. But here the channel matrix is very sparse. So the complexity of the memory match filter is only PA, and P is the number of non-zero elements in each row. So it's similar to the number of paths in the communication systems. So it's much less than the length n. So we can compare these three complexities. As you can see that if P is much less than n, then FFT dominates the complexity of the whole algorithm. So it's quite low. So the complexity of CD memory MP is very, very low. So here is a comparison between the IFDM and OFDM, OTFS and AFDM. So OFDM works on frequency domain, and it has a diagonal channel matrix in frequency domain for the static multipath channel. And the OTFS works on delay-Doppler domain, and it has a equivalent sparse channel matrix on DD domain. And AFDM is similar. It has a sparse channel matrix in the approximate sparse channel matrix in the DAF domain, discrete affine frequency domain. And all the complexity of these are approximate to almost n log n is the complexity of FFT. But IFDM works on interleave frequency domain. The equivalent channel in IF domain is random and dense, not sparse. And its performance is the relative performance here is the IFDM better than AFDM and better than the OFDM. And here is the detection, comparison of the detection. We have a linear MMC detection and Gaussian mesh passing. And the Gaussian mesh passing is unstable, and some cross-domain OMP and DD domain OMP and DD domain memory MP and cross-domain memory MP. But the cross-domain memory MP has the lowest complexity is given by this formula, and the performance is almost the best. And here I show you some simulation results. First, we do the MIMO QPSK multipath channel, and the speed equals to 0. And we compare the IFDM with low complexity CD memory MP detection with AFDM with high complexity OMP detection, and the OTFS with high complexity OMP detection, and OFDM with high complexity OMP detection. And we can see that IFDM has a significant improvement on the BR performance. You can see here. And then we increase the speed of then we let the speed equals to 300 kilometer per hour, and we still consider minimal QPSK, and we can see like here OTFS has a significant performance improvement compared with the static or the 10 invariant channel. But it still has a 5 dB gap between the IFDM and memory MP. And we can also consider other schemes, for example, AFDM, and OFDM with OMP or memory MP. Both of them has performance loss. This figure gives the complexity compilation. We compare the running time of the memory MP and the OMP and the VMP and the other different detection schemes, and we found like the memory MP has the complexity of memory MP reduced more than 100 times than the OMP and the VMP. So based on this, we can conclude that IFDM outperforms OFDM, OTFS, AFDM on the BR performance and the complexity. But it's based on the specific detection algorithm, not this conclusion not applies to any detections. So here we just do the simulation result for the OMP and the memory MP detections. So the property of IFDM is that, or the random unitary modulation removes the red unitary event matrix assumption in AMP type algorithms. So it means that it works for arbitrary channel matrix, including but not limited to 10 wand multiple channels. So here is the overview. So first is the whole unitary space for the transform matrix design. And then is ML optimal space. It means like if we use ML detection and the performance is optimal, the performance is optimal. And then this means that it's AMP optimal. It means that we can get a global optimal performance with AMP detections, since AMP detection is low complexity. And this area belongs to IFDM. IFDM means we use a specific random matrix that is interleaved frequency FFT, interleaved FFT, and it has a low complexity with memory MP detection, and it is asymptotically optimal. And both these areas are optimal, asymptotic optimal under certain conditions. And here are assumptions. We assume that the system size is very large, and it has a unique a fixed point of the state evolution. And here the optimality means the replica optimality. And as I show you, the proportion of this area goes to 1 when the dimension of the system goes to very large. And here is a high complexity area, but still optimal. For example, we use likelihood detection, and we can get the optimal performance. But the proportion of this area goes to 0 when the dimension is very high. And here is the suboptimal area, and the proportion is also goes to 0. And unfortunately, OFDM belongs to this area, since as I show you the simulation result. But OTFS and AFDM, actually there is no efficient detections. The example is that if we use AMP detections, it is suboptimal, as I show you in our simulation results. But if we use likelihood detection, we don't know. So we don't know it is optimal or suboptimal. So we are unclear. We are unclear of that OTFS or AFDM belongs to the suboptimal area or the likelihood optimal area, but it not belongs to this area. Since we do the simulation results, we found like this is suboptimal. Is the performance is worse than the IFDM. So this is an overview of the IFDM or OTF or SAFDM and OFDM. So then is the last part. So as I mentioned to you, so we need to design the encoding and decoding for the linear systems, and how to design a code to approach or achieving the channel capacity of linear systems is still unclear. So therefore, we propose a capacity optimal coding principle for the linear systems. The challenge is that if we just use a seesaw or a seesaw coding or a seesaw AWGN optimal capacity achieving encoding, but in the linear systems, this is suboptimal. So the solution is that we propose a capacity optimal matching coding principle for the linear systems, and I will show you. First is the capacity area theory. So as I mentioned to you, the memory MP or the AMP type algorithms can decouple with two local processors, and we do the iteration between the two local processors, and we can use the state illusion to describe the performance of each local processors, and then we can get a transfer function of this of the detection here. Use this line, and we can also get a transfer function of the demodulation or nonlinear estimate. I use this line, and after that we can prove that the area covered by the lower bound of these two lengths, that is covered by the red line. You can see here is exactly the channel capacity of linear systems. It means that this area equals to the mutual information between the receiver and the receiver received signal at the linear systems and the signal X. And here are assumptions. The first assumption is that we request the channel matrix should be relatively invariant matrix. This assumption can be relaxed or can be ensured, can be guaranteed by IFDM. So we can remove these assumptions. And the other assumption is that we require the system size is very large, goes to infinity. And the last assumption is we assume that these two transfer functions has a unique fixed point, has one intersections. So then we do the joint detection and decoding, and next I will show you some very nice properties of this scheme. So so after we can consider the encoding, so we include or combine the demodulation and the decoding as a whole nonlinear estimate. So it includes demodulation and the decoding. Since we include since it includes decoding, we have decoding gain, right? So the decoding, the transfer function of this part, I just call this as decoding transfer function. Use this red line. So it is better than the demodulation since we have decoding gain, right? So the red line decoding transfer function is outbounded by the demodulation transfer function. And the second is that we do an iteration between these two processors, and this is the blue line. So we do the iteration between the decoding and the detection, and we need to get an error-free performance. It means like we need to go to 0. So there is a tuner between the detection line and the decoding line. So it means like the decoding line is also outbounded by the detection. And the last is the area covered by the decoding transfer function. This red line is the code rate. So we want to get the error-free performance and maximize the code rate. So what is the optimal case? The optimal case is that we want to maximize the achievable rate or the code rate that is the area of this area. And the optimal case is that we let the decoding transfer function approach their upper bound. Then we maximize this area. Then we get the maximized achievable rate, right? So this is the matching coding principle. So the optimal decoding transfer function is given by this, the lower bound, the lower bound of the these two transfer functions. And as I mentioned, this area is actually the channel capacity. So it also means that in this case, the achievable rate of magnetic detection achieves the channel capacity, linear channel capacity. So next, let me show you some very interesting area properties. First is the area is the constant capacity is given by this the lower bound of these two lengths. And the name we consider a specific case that is a cascaded detection, demodulation, and the seesaw decoding. And there is no interaction between these modules. And you can see first we do a detection here, then we pass the message to the demodulation. We do a demodulation here. Then we do a decoding. Then we go to the zero, get an error-free recovery. Then we get the this area denotes the achievable rate of this system. So how about we do an iteration between the detection and the demodulate? Then we get a optimal detection converges to the optimal detection point B. Then we do a pass to the seesaw decoding. Then we go to the zero, get an error-free recovery. So this area means that the iteration gain of the achievable rate in the case that we can do iteration between these modules. So how about this? If we optimize the decoding for the linear systems, and then we do iteration between the decoding and the detection, then we can get an additional area by this area. So it means like we can get a better performance or better or larger achievable rate if we optimize the channel code. And here we consider the discrete constellation, for example, QBSK and the Quan. This is a transfer function of the discrete transfer function. But if we consider Gaussian, a Gaussian singularity, then the Gaussian detection transfer function move here. So this means that we get an additional achievable rate by this area. So this means the shaping gain of the Gaussian singularity. So if we consider another system that there is no interference between the transmit symbols, you can see here, this symbol just transmit to the antenna 1 and this X2 to antenna 2, and there is no interference between X1, X2, and Xn. And in this case, we can get an additional area of the achievable rate is this area. So this means that is the performance loss or the rate loss by the interference between the symbol interference. So if we consider the non-interference case and the low channel noise, it means the noise free and low symbol interference. In this case, the achievable rate of the system is the area covered by this red line is the transfer function of the demodulation. So we get an additional area by this of this area, additional area given by this. So this area means the rate loss caused by the channel noise. So this is next is the summary of all the AMP type algorithms. So AMP is limited to ID Gaussian matrix, and OMP requires high complexity MMSE. Also similar, tube MMSE requires high complexity MMSE, but it is also limited to Gaussian signaling. If we want to use tube MMSE for Gaussian signaling, for non-Gaussian signaling, it is suboptimal. But the memory MP works for general arbitrary singularly, and it works for general unitary random matrix. This assumption can be relaxed or removed by use IFDM, and it is also a non-Gaussian capacity optimal, and the complexity is quite low. Here is the achievable rate comparison between the memory MP and the tube MMC. We consider 16-Quan constellation, and this is the Gaussian capacity. And we can see that tube MMC is suboptimal for discrete non-Gaussian signaling. And this is the achievable rate for CISO code, and this is the optimized code. And we can see that the optimized code has a significant improvement in the achievable rate than use the CISO code. So it means that the CISO AWDM code is suboptimal in linear systems. This is the performance comparison of the memory MP use optimized LDPC code, and they are here, and also OMP, high complexity OMP with optimized LDPC code, and they have almost the same performance, but the complexity of memory MP is much lower than OMP. And these two layers are the detections with unoptimized is the regular LDPC code and the irregular LDPC code. So there is performance loss if we just use CISO AWDM code. And actually, before we propose IFDM, we also use the memory MP detection for the MIMO OTFS SCMA systems. And since in MIMO OTFS systems, in the DD domain, the channel matrix is sparse, so we can use memory MP for the detection, and the complexity of memory MP is also very low. And here we get the same performance of memory MP at the high complexity OMP for the OTFS systems. You can see here, but and we have a significant a performance gain named the convolutional Gaussian multipathing and the EP algorithms. But it should be pointed out that the CISO OTFS, here we consider MIMO OTFS, since the channel is not right unitary in random matrix. If you don't use IFDM, you just use OTFS, the channel is actually not right unitary in random matrix. So memory MP is not stable. So if we consider CISO, so memory MP is not as stable as OMP. But if we consider MIMO, memory MP is more stable. Here we have some new results on the IFDM. Here as I mentioned, the whole complexity of memory of IFDM or memory MP is dominated by the FFT. So if we use a very large FFT, the complexity is also very high. So to solve this issue, we propose a low complexity interleaved block sparse transform. Interleaved block sparse transform is given by this figure. It means that we just use some small FFT matrix. Then we do an iteration between the interleave between the laws of this matrix. Then we can get a very good performance of the IFDM. As you can see here, we use 4 FFT with a length 4,000. But here if we use IBS is a block sparse transform with a length FFT length 100. The performance is almost same as the 4 FFT matrix, but this one has low complexity. So it means like IBS T can realize performance and complexity trade-off. We also do some simulation with not FFT. You can use other transfer functions, for example, Hartman transfer functions. But based on all simulation results, the Hartman transform is not as good as FFT, but the hardware complexity of Hartman transform is much lower than the FFT. Okay, we also extend our memory MP to the distributed memory MP. It means that each receiver receives a part of the Y. So here, this node just received Y1 and this node received Y2, and they are not centralized. So we propose a distributed memory MP algorithm, and to ensure that the performance of the distributed system can also converge to the centralized case. This is a simulation. And also we extend the result to the generalized linear systems. Generalized linear system is that there is a non-linear operator here. For example, clipping, the ADC, or the phase retrieval, something like that. And this is a summary. So in this talk, we discuss the IFDM modulation, and we introduce the cross-domain memory MP for the detection of IFDM, and finally we introduce the capacity optimal coding principle for the IFDM with memory MP detection. Okay, that's all. So if you have any question, I will be happy to answer.
Thank you, Professor Liu. That's a really great talk. It's very informative and quite different from what we had so far, because I think what you have proposed is completely from a new perspective in waveform designs, and it's really, really informative. So I have collected several questions from the audience and from myself as well. So I hope you would have some time to answer them.
Okay.
Yeah, okay. So it's actually the first question is about the example you presented. When you are mentioning that you added this rotation matrix at the beginning for this diagonal matrix, such that your performance is improved, right?
Yes.
Yes. I think there is a potential, I'm not sure. So like I think another alternative for this rotation metric is actually doing power allocation for this S1 and S2. And this is normally what people do in OFDM. They call it power allocation or resource allocation here. So I wonder, because the performance loss based on my perspective, my understanding is due to this channel inversion. So did you compare if you do a proper power allocation between S1 and S2, which will be a better performance?
Yeah, it's a very good question. Actually, here the system, we assume that the transmitter uh, uh, does not know the channel state information.
Right.
So you can't do the power allocation.
That's
So
true.
if you know the channel state information, then you can do the power allocation. You can get a better performance than this scheme.
Yes, yes, I agree with you. And that's actually one of the questions I want to ask. I have also a follow-up question that assume that even if you are knowing the channel state information, but if you are doing, for example, a linear power allocation scheme that requires that you assume that S1 and S2 are Gaussian distributed. However, when this is not Gaussian distributed, do you think this the thing you introduced will outperform this power allocation?
Yes, we already have some simulation results. Actually, we are doing this work.
Okay,
It's a very
okay,
good
that's
work.
great. Yes.
Very good question. Very good question. Yes, the answer is yes. So
Okay.
Gaussian power allocation or the theory is optimal for the Gaussian signaling, but
That's
for
right.
non-Gaussian signaling, yeah, the suboptimal. So we have some simulation results, and if we do a specific power allocation for IFDM, you can get the best performance for non-Gaussian signaling case.
I see. Right. There's
Yes.
also a paper from Professor Cheng Xiao and a lot of famous people in that paper. They are doing power allocation for non-Gaussian signalings. I wonder, I'm really curious about the results. We can discuss offline, of course.
Yeah. Thank you. So
Okay.
it's a very good question. Yes,
Thanks.
actually, it's still in preparing. So if we have some new results, if we can share with you.
Okay, thank you so much. Thank you so much. Okay, another question is actually also related to this. When you are mentioning that AMP is actually approaching the capacity, I realize there are some potential works for this sparse superposition coding that
Yes.
they use some coupling between these like code assembles and then apply AMP, and they show that actually is a capacity achieving. So I wonder, is this approaching and achieving the difference between them is do you need a coupling somehow to compensate this loss?
Yeah, it's also a very professional question. Yes,
Thanks.
they are different. Let me show you the difference.
Okay,
The key point is that for the SR code, they use special coupling uh, to approach the capacity of AWGN seesaw channel,
that's right.
not
Yes.
linear channel.
Oh, okay.
They work for seesaw channel. But here, all work prove that if you design a code like this, you can approach the capacity of the linear systems. Uh,
Mhm.
in fact, we found that if we let the channel matrix be identical matrix, then all results reduced to the SR code.
I see.
Uh,
That's very
but
interesting.
SR code are used to design a code match with this straight line. So
Hmm.
you can also find uh, another new codes. Like if you can approach this land, then you can approach the capacity.
I see. Thank you very much. That's great. Okay.
Oh, very
Um,
nice question. Mm.
thanks. Another question is about this hard metrics that you introduced for
Mm.
for IFDM, right? So when you're mentioning
Mm.
this hard metrics can ensure this red unitary invariant property, I wonder, do you have any assumptions on the, for example, frame length or the constellations?
Sorry, I didn't get your point. You
Uh,
mean,
Sorry, like when you are assuming that there's a red
yeah,
unitary invariant case,
rescue,
right?
yeah,
Yeah.
yes, like
Of
you
course,
enjoy
that's
alignment. Yes,
but like since my understanding is like this Haar matrix is a random matrix. So
yes, random
if I
matrix.
do not
Mm.
have a very long block length, it may not
Yes,
preserve good randomness. So
yeah,
will that
yes.
affect your performance?
Yes. Yeah, we have performance loss if you consider finite length random matrix. So, for example, you just
Okay.
you construct a matrix given by IF by the interleave
Mhm.
frequent FFT.
Mhm.
In this case, if you consider small system size, then the performance is not as good. There still has a gap. If there still has a gap between the state illusion and the simulation.
Mhm.
So here we assume that we still all the theoretical results assume that we consider very large system size.
I see.
But in my opinion, the performance is still good enough for small size systems.
Right.
But
Right.
but uh, but we need to very carefully design the random matrix.
Okay.
Maybe this way IF is not efficient anymore. You can find other ways to construct the random matrix.
Right. So, I wonder, do you think this is maybe it's a useful to characterize this so-called ergostic performance in the sense that you are
Yeah,
plotting
yeah,
a lot
yeah.
of different random ensembles to have an
Yes,
average. Okay, I see.
yes, I agree with you.
Thank you very much.
Mm.
Uh, okay, I also have some questions actually collected both from the audience and myself. It's about the performance of some communications. You
Mm,
have shown that some
mm,
performance about the bit error rate, which is of course very important for communication, but there are also
mm,
other performances. For example, there was one question from Messi. He mentioned that about when you are introducing interleaving there, it may potentially have a big impact on the bandwidth it costs. Did you have any constraints on the interleaver design, or have you ever mentioned or evaluate this performance?
Okay, it's a very good question actually.
Mm.
Yes, here when we do the dual simulation results, we just use a random interleave, use MATLAB, that use a MATLAB code. But in practical systems, you should be careful. You should carefully design a very simple interleaver. And I know there are many interleavers in the coding. For example, tuple code, and also in IDMA systems.
Mm.
Uh, um, we have to do some simulations. We found like maybe the situation may be different. You need to redesign the current interlevers for specific for IFDM,
Mm-hmm.
and to ensure like is very simple and friendly to the hardware systems.
I see. Right.
Mm.
Okay. Also, there's another question following up. This is about the channel coding when you are introducing about this optimal designs. So when you are considering doubly selective channel, especially for example, coded OFDM and coded OTFS, it has been shown that their performance are relatively similar, right? So I wonder, even when you are showing that IFDM may have some potential performance gains, if you apply coding and with the same coding, perhaps with other waveforms, do you have a comparison for these two?
Yes, we have as I show you,
Okay.
but I didn't show the result in this slide. So we already have some results.
Right.
The key point is that if we want to achieve the capacity, we need an exact correct state solution, right? Since all the coding design is based on the correct state solution, if you don't have a correct state solution, you don't know how to design the code to match
Right.
this net. So, but IFDM ensures the right unitary event in the property, then we can get a correct state solution. But if you consider OFDM and OTFS and the AFDM, then the state solution is not correct. If you still assume that the state solution is correct and design the coding for the OTFS or AFDM, there is performance loss.
I
This
see.
is all results.
Right. That's a very good point. Very interesting. Yeah, I think that's a quite a good answer for that. I have a final questions perhaps. So
Okay.
for IFDM, right? So would you like to summarize your big contribution just in a very short, concise summary? So why this is a differ from most of the existing waveforms?
My point is that the principle is different. So the
Exactly.
previous OFDM, OTFS, and AFDM try to diagonalize or sparse the channel matrix
Yes.
to want to the goal is want to get a simple detection,
Mm-hmm.
since it's very hard to efficient detection for the dense matrix. But
Yes.
thanks to memory AMP or memory AMP type algorithms, we can deal with the dense random channel matrix. So IFDM is much different. The goal is to design a random and the dense matrix, but we still have a low complexity memory AMP detection
Yes.
for this and can approach the global optimal performance with no complexity and the certain conditions.
Yes.
Yeah.
That's a really good summary. I would also like to just add a little bit of my own understanding for this. It's like uh, I think this is a very different way of designing waveforms, right? So as you mentioned, you are actually you are intentionally introducing something to make the matrix very random and dense. This is very different. So I guess that IFDM may have a big advantage in some cases where the channel does not hold any sparsity at all. So it is dense already. So conventional waveforms may not work very well. So therefore, I think this new waveform is actually quite interesting and very different from most existing designs. So thank you very much for this great
Thank you. Thank you.
introduction and also this great presentation.
Thank you, thank you. One last point is that since IFDM is just a beginning, in my point of view, we just focus on the data detection or data transmission. Assume that the channel matrix is already known, but in practical systems there are many issues. For example, we need do a iterative detection. Namely, there is a delay in the real communication systems. How to solve this issue? And for example, how to do the channel estimation is still another issue. So can we find a better channel estimation under the IFDM framework? And the other is that how to design a very simple or hardware-friendly interleave maybe another issue. And also, as I showed, the modulation. The key point is to design a random matrix. Is not limited to IFDM. You can use other random unitary matrix, hardware, hardware transform, and other. Maybe there are many works to do, in my point of view.
Okay, that's great. Thank you for introducing some new directions for our waveform and the physical layer researchers. That's very important. Okay.
Thank you.
So thanks again for joining us today, and thank you all the audience for the support and the kind of questions. Okay, I will see you guys next time. Okay.
See you. Thank you.
Bye bye.